The topic of this lecture also is lithium ion battery. It is basically a continuation of an earlier lecture. We were discussing about the various aspects of lithium ion battery, its importance, the constructions, what are the materials involved, and we wanted to discuss what are the alternative materials involved or the possible materials in addition to the anode, which is normally the lithiated or lithium intercollected graphite, and the cathode is once again lithium intercollected cobalt oxide. So, let us see whether we have alternative materials and one can use a improved version of the battery, and of course, one can also see whether less costly materials can also be used replacing cobalt. We discussed this particular figure in which many different oxides or many different other compounds have been plotted both in terms of the voltage or the potential which can be generated out of it, in terms of the lithium and the capacity. So, there are large number of different materials have been presented here, and as was mentioned earlier, lithium cobaltite is somewhere there. Then we have alternative materials, material structures. In fact, we have discussed 3 different structures. One is the layered structure oxide, cobalt oxide, COO2 is an example of that, is an important member of that, and then we have a spinel structure, which is basically Mn2O4 structure, and the third one is a olivine structure. The important example is LiFePO4. These are 3 different structures, and many of them have substitutions in them, and they can be used or they have potentially they can be used from this diagram. So, 3 members which are very important here. One is LiMnO2, and then a variation of that in which some substitution have been made with nickel, and COO2 structure, in which the COO2 structure CO has been replaced by partly manganese, partly nickel, and then you have LiFePO4 structure, and this is Mn2O4 structures. Others are not, although for theoretical purposes they are important, but they are not that important at this stage. So, these 2, 3, 4 different compounds are being researched on very extensively. In addition, one more compound I will draw your attention to is Li45O12. Li45O12. This, although has a very low voltage, in fact 1.5 volts or so, also capacity is not that high, but it has a different, it is important in a different context. We will discuss that also at a later stage. So, these are few compounds which are of importance to us, and we will see how they can be utilized in the lithium ion battery. When we are talking about these kind of compounds, different compounds, the very first thing one has to find out what is the binding energy, and that binding energy with the lithium actually provides an idea of what kind of voltages one can expect. So, in that context, these are the different compounds, some of them have been plotted over there, and lithium manganese oxide, or the spinel variety of lithium manganese oxide, has the highest binding potential, binding energy, and also the highest potential. Lithium cobalt oxide is here. Okay. So, they are quite comparable. Lithium iron phosphate is slightly lower, the voltage is slightly low, and then you have here lithium titanium oxide. Okay. In fact, it is actually lithium 4/3, titanium 5/3, oxygen 4. Okay. So, if you multiply by 3, in fact, it will be lithium 4, titanium 5 and oxygen 12, which was shown in the earlier picture is here. It is the same thing. Okay. So, this is fairly low, about 1.5 volts, whereas this is fairly high, is about more than 4 volts, which is comparable to lithium cobalt oxide. So, the binding energy are compared in this manner. Now, considering all these, we have, particularly if you are talking about cobalt, if you are concentrate our attention primarily to oxide, not like sulfides and phosphides. These are phosphates. These are some of the oxides containing transition metal oxides, some transition metal oxides, right. Transition metal oxide has a role to play, because we have seen earlier in case of cobalt, there is a valency change from 3 plus to 4 plus or 4 plus to 3 plus. So, obviously, our attention has to be given or be paid to transition metal oxides. So, these are some of the a list of transition metal oxides which has a potential application to replace cobalt oxide and in the lithium and battery system. Now, of course, all of them are not devoid of cobalt, some of them have been, cobalt has been partly replaced by nickel here, partly replaced by manganese, and it is also partly, I think there is a repetition here. This can be removed. Right. So, you have because there has been basically an attempt to reduce cobalt, because cobalt, as I mentioned, it is a costly or economic, not an economic material. So, if you can replace, completely replace or partly replace, that is the basic idea. So, here nickel cobalt has been replaced partly by nickel, partly by manganese, and also here partly by nickel, partly by manganese, both nickel and manganese has been used, and here completely removed, cobalt has been completely removed both by nickel and manganese, and then also once again there is a mistake, I believe. Let me also remove that. Right. So, both nickel and cobalt have been replaced by cobalt has been replaced by nickel and manganese, right, and here it is only manganese, and this has of course is a different the same structure. This is the Mn2O4, Mn2O4 will have a spinel structure, but this is also the same structure. Okay. So, these are some of the layers mixed oxides, and here this is the characteristics charge discharge characteristics of a particular compound, which is a spinel structure lithium manganese 4. Okay. Manganese 4 spinel structure we have seen earlier. This is the charging characteristics of that, and these are the discharge characteristics under different conditions of discharging. Now, discharging is normally done at a rate of designated like C by 2, C by 5 or 20 C. Now, just to have a discussion on that, what we mean by this is what we call the charge rate or discharge rate. The charge rate is denoted as a C or C rate, and signifies a charge or discharge rate, okay, charge or discharge rate equal to the capacity of a battery in 1 hour. For example, As you possibly you are aware, the capacity of a battery is normally given as ampere hour. Okay, that is the total amount of energy which it can accommodate. So, if you have a capacity of a particular battery is 1.6 ampere hour, the C 1 C it becomes 1.6 ampere. That means, in 1 hour you charge it fully or you discharge it fully at the rate of 1.6 amp. So, if you draw a current of 1.6 ampere over a period of 1 hour, then this is the total capacity of the battery, and this becomes then the C. A charge rate of C by 2 means actually 0.8 ampere, 0.8 ampere, half of 1.6 would be needed for 2 hours, and a charge rate of 2 C, that means double the value of the capacity, we have to charge 3.2 amperes would need 30 minutes, half the minutes to fully charge it. So, it is basically the rate at which the current is being drawn from the battery, or it is being introduced, or the charge is introduced in the battery or recharge the battery. So, that is what is known as C rate. It assumes that the battery, of course, whenever we are doing it, it assumes the battery is 100% efficient at absorbing the charge and can support the applied rate. That means, if you charge it at a very fast rate, for example 2 C or 10 C, 20 C, that means you are charging or discharging at a very fast rate, and the kinetics may not support it. So, there may be a breakdown of the structure. So, otherwise this can be done. In fact, that is one of the criteria when a battery is tested, that is one of the criteria, how fast one can discharge it, how fast one can recharge it, and so on. So, this provides a criteria or a parameter, what is the rate of charge, what is the rate of charge recharging or discharging. So, under this context, if you go back to this particular curve, you can see the charging is being done at a C by 2 rate, okay, half the total capacity, and then discharging has been tried out. Discharging has been tried out C by 5, and in this is increasing 20 C, 20 times the overall the capacity of the battery, okay. And even then one can, although the voltage will drop obviously, because charging rate increases and the voltage will certainly drop, but even then you can get a fairly high specific charge. So, MnO4, LiMnO4 is an alternative cathode material replacing LiCO2. Okay. So, these are some of the typical experimental data which has been taken from the literature, of course, and these are the possibilities. Okay. So, one can charge at a very fast rate as well as discharge at a fairly fast rate. This we have discussed, and the same thing once we plot as a discharge rate is the C and the discharge capacity. So, lower is the discharge rate, obviously higher will be the capacity, but higher is the discharge rate, the lower will be the capacity. Okay. So, you have to find out at what rate, what will be the optimum condition under which the battery can be utilized. Okay. So, normally 2 C, 5 C, not so low. Okay. So, these are the typical characteristics of the particular cathode material which has been used, of course, in conjunction with the graphite anode. Now, here is a comparison of few different cathodes. Reference is, of course, the LiCO2, and these are number of cycles. Initially, of course, the discharge capacity is high, but as the cycle chain increases, it becomes lower. Although we are talking about 300 600 cycle capability, but that is certainly it gets lower and then gets stabilized. Okay. It does not continuously decrease, but compared to the initial capacity, certainly the capacity is lower even after about 50 cycles. So, that is the typical one of the typical characteristics of the cobalt oxide cathode. Now, compared to that, there are alternatives here which we have just discussed. One is spinel type, LiMn2O4 is one of them, and LiX MnO2. This is the same structure, only thing cobalt has been replaced by manganese. So far as the electrical characteristics is concerned, of course, is quite good. That means, it remains stable, even at the starting capacity for a long enough time or large number of cycles. The Mn2O4, the spinel structure itself has a lower capacity, but it is remains constant over a large number of cycles. So, compared to lithium oxide, it is certainly better in certain sense, in this particular sense at least, so far as the cyclability is concerned. And the layer structure MnO2, if you replace cobalt by manganese, also has a better property. However, there are certain disadvantages, of course, so that these are not still commercially being used. Commercially, the most important one is still the lithium cobaltite. The more promising one, of course, is LiFePO4 structure, which is as I mentioned is the olivine structure, orthorhombic symmetry, high thermal stability, inexpensive because iron and phosphorus, these are the two elements here in addition to lithium, environmental friendly, there is no cadmium or anything like that, and lead is also of course not there, and high capacity is about 100 milliamps per hour, which is quite high, and excellent cycle life. So, this is another compound in a different crystal structure or a different structural with having different structural characteristics. This is also a good material, and the typical discharge cyclability curve is like this. Here you can see about up to 300 cycle it remains more or less constant. So, in that sense this is one of the LiFePO4 iron lithium iron phosphate is one of the most promising material so far alternative to cobalt oxide. Now, there has been a lot of consideration or research work is still going on the alternate anode material as well. Okay. So, this is our currently used material, it has been written in a different way, is 1/6, it is actually LiC6. Alternative materials are in the same group, the group 4 elements, okay, as carbon. So, these are either silicon or tin, lithium containing silicon carbon nanocomposites, which have also much higher capacity, that I will see. So, it is the same group material, same group element as carbon. Of course, they do not have the same structure, the structure is different, silicon structure is different, and structure of tin is also different, whereas carbon is a different structure, but even then these materials do have some property of accommodating lithium or intercalating lithium as in case of carbon. However, these materials undergo excessive volume change on lithiation and tends to destroy the structure. This is one of the another very important criteria. This is another very important criteria for choosing the right kind of material. Now, whenever you are introducing lithium into the structure, it certainly there will be some expansion, because now compared to the virgin material, there will be always some volume change, and the lattice parameter will be increased, and as a result there will be volume change. So, this volume change is certainly a very important criteria or a problem for actual practical application. So, that has to need to be considered. It happens in all the intercalation compounds, but lithium cobalt or lithium graphite is acceptable, but whereas the other things also need to be understood, how much one can accept the volume change. This is a typical performance of a tin carbon composite anode. Okay. We have seen carbon anode, graphite anode can be replaced by some other composites including other metals. So, this is a very good characteristics. Once again we have very constant value of the charge discharge characteristic, they are exactly in the same capacity, and it can extend up to 200 cycles quite easily, and it can go beyond, of course. So, this is a typical tin carbon composite anode, okay, tin graphite composite anode. Of course, one has to also remember, although we are talking about graphite, there are various kinds of carbon which can be used, and there are I am not going to the details of that, but depending on the preparation condition, depending on the morphology of the material, the structures or the properties of the battery certainly changes quite extensively. Now, in addition to tin carbon, there are other materials as I just mentioned, like silicon. Silicon is also a composite, silicon is a compound which can be directly used, or these are some kind of nano composites actually, where graphite and silicon can be used together. Then in addition to some more complex materials like silicon titanium nitride carbon composite, or silicon titanium diboride carbon composite. So, these are also can be used or can substitute the virgin graphite, and so these are again some of the characteristics, of course, for a limited period, and one can see silicon, although it has a very high capacity, you can see the range of this capacity as much higher. Okay. If you compare the earlier values is about 500, 400, 500. Here silicon has a value of at a low initially it has a value of almost about 2000, but it goes down with cycling and stabilizes somewhere around 400, okay, 400 milliamps per gram. Whereas, if you take composite silicon carbon composite, this is happens to say pure silicon. So, pure silicon although has a very high binding energy and therefore, a much better capacity, but then it drops off very sharply with cycling, whereas these two materials, particularly the nano composites of silicon carbon, these are actually nano composites of silicon carbon, they have a fairly stable capacity over a large number of cycling. Silicon titanium carbide, nitride carbide, and titanium nitride carbon and silicon titanium diboride carbon also can be used for this purpose, and it has a lower capacity, but stable with cycling. Well, these are when you talk about different compounds, one also has to have a theoretical values of capacity, one can find out from the binding energy, and these are different values of the capacity, theoretical values of capacity one can expect from different kind of compounds. Here is only tin, silicon, lithium, lithium oxide, lithium, this is again tin, okay, and so on, silicon, carbon, Li6. This is the currently used compound. Compared to that, one can see the capacity is much higher, okay, compared to much higher compared to Lic6. So, other materials have much higher compound or higher capacities, but these are all theoretical values. So, when somebody is screening the different material, one can look at the theoretical capacity, but many of them are practically not feasible, really not feasible, and that is why Lic6 is still a material of interest for the practical devices. However, many research is going on different other compounds as well. So, these are some of the results of that investigation. One of the problems is once again, as I mentioned, the volume change. In fact, Lic6 is a fairly large volume change, but that is acceptable, whereas lithium, aluminum, these are lower volume change, but even then there are, because of some other problems, okay, because of some other problems, they have not been used so far or being investigated, investigation stage only. Nano effect is there in this material, in fact it is very important. One of the major investigations or research area or research interest is in the area of nano, okay, whether the materials can be used in the nano powder form, and they have some effect on that. And here only in case of a particular spinel type of compound, the LiMn2O4, if you prepared in the micro bulk, in the sense micro fine powders, and these are nano fine powders, you can see a significant increase in the capacity, specific capacity here. Once again it increases almost by 50% or more. Okay. So, in fact most of the research is going on here. What is the effect of nanomaterials or nanostructured materials in improving the properties of the lithium batteries. Okay. So, this is one example where nanomaterials have improved the properties. Well, this is once again has been taken from some literature here. In the this is how the construction of the cells are made. Okay. We have seen large number of coin cells, sometimes they are called coin cells, sometimes called button cells, and very thin cells just like a metal tablet, and but it contains a large number of components. That is the reason why I am showing this. This is the top cover, which is a top stainless steel cover, which acts as a negative terminal. You have an insulation ring, insulation gasket, normally may be a Teflon ring, okay. And this is the top cover and this is the bottom casing. So, these two in between you have a large number of thin sheets or thin layers. This is your positive electrode, that is lithium cobaltite, that means the cathode. This is the cathode, and this is the negative electrode. So, this is basically, this is the single cell. Okay. You have a separator, a very thin separator containing the electrolyte. This is the layer, very fine layer of graphite, and this is a cathode layer, the positive electrode, and they are all sandwiched between these two casings. Okay. And this is the electrolyte, sorry, no, this is the liquid electrolyte soaked, or the porous material soaked in liquid electrolyte. Okay. So, this sandwich structure actually forms the cell, and these are actually stainless steel spacer, this is a spring, and finally through this it is connected to the top layer. So, this becomes your negative terminal, this becomes the positive terminal, and in between you have an insulator, insulating gasket, which separates the top cover, electrically separates the top cover and the bottom cover, bottom casing. So, that is how one makes a coin cell, which is extensively used in many electronic gadgets or electronic devices. In addition, of course, one thing we should also mention, all these things are actually produced in powder form, okay? Whether it is a lithium graphite or lithium cobalt, both of them are prepared in actually in the powder form. So, they are coated on some substrates. Normally on this side is a copper foil, and on the other side there is a aluminum foil. So, they are actually screen printed on this. So, basically the materials are in the form of powders. Okay. So, it is not in the form of discs or any plates. So, they are powders coated on some substrates. So, therefore, nano powders has a very important effect, because nano size powders increases or decreases the lithium mobility, or in fact it increases the lithium mobility, the interaction distance becomes finer, and therefore, there is an enhancement in the properties. So, since we are talking about powders only in the solid state, so certainly the nano powders has a much finer, much larger specific surface area. So, the interaction becomes better, and the charge transfer becomes much faster. Okay. So, that is one of the considerations, and that is what we call the coin cells. The another, of course, there are very different kind of shapes of the lithium cells, like many other rechargeable batteries. The standard kind of battery here is cylindrical. Here the, of course, they are produced in a completely different manner. It is a similar to tape casting process, very similar to tape casting process. So, there are rolls of the three different sheets. One is the cathode and the anode and the separator. So, all of them are rolled together and then in the form of a coil, put in the form of a cylindrical shape. So, that is a different, these are not discrete sheets, but there are continuous sheets which can be rolled together to form a cylinder. So, that is how the cylinder is prepared. Well, with all this, let us come to the discussion of major applications. I am sure most of you are familiar with that. These are cell phones. One of the largest applications are different forms of cell phones, iPhones and iPods and all kinds of electronic gadgets, communications and so on. Other important area is the laptops and notebook computers. Almost all computers, particularly laptops and notebooks, do have this lithium-ion batteries, rechargeable battery, that is one of the very important component of the whole system. The digital camera, almost all digital camera requires battery, and they are all rechargeable battery. Earlier rechargeable batteries were nickel cadmium, now they have been replaced by lithium batteries. Many entertainment electronics also requires lithium batteries. Camcorders, that also requires lithium batteries. These are all low power applications. You are not drawing very large currents. So, the rate of discharge is relatively low, and however, if you go to rest of the applications, the rate of discharge and the power capacity is very high. For example, if you are talking about power tools require a large energy, but it can be made out of lithium batteries. Then the most important driving force for development, the further development of lithium batteries is here. It is the electric vehicles or the hybrid vehicles, sometimes hybrid vehicles, all those prototypes are there already. So, the main driving force currently for development of the lithium ion battery is the electric vehicles for the future, and how much and the requirement is completely different compared to the current range of applications where you are requiring only low discharge rates. Here you need a very high discharge rates, and total capacity also have to be very large, so that the range of the vehicle can be increased to a reasonable extent. So, for that you need a completely different materials as well as different structures of the powders, not the crystal structures, but the morphology of the material, and in that context nanotechnology is playing a very important role. So, nanotechnology, particularly nano powders of different shapes and sizes of the same material, maybe lithium cobalt or graphite or other spinels or the olivine structures, the phosphates, iron phosphates and so on. They are primarily concentrating, their research is primarily concentrating in the area of morphology of the powders, how the morphology of the powders can influence the properties. So, not only the crystal structure, but the morphology of the powders, the fineness, the shape, size, the surface area, all of them have a very important role to play in looking at or in the performance level. The other area, this is also same for if you are talking about the defense and space applications, because the energy density is very high, okay, per kg of material you have a very large energy density, much larger than any other form of battery, and therefore, space application is a very important application where you need space vehicles, and weight is a very important consideration there. In defense also, in some of the applications, particularly missile applications and so on, you have a tremendous importance of lithium battery, because one of the major driving force is the power to weight ratio. You have a very high power to weight ratio, and therefore, in all these applications, airborne systems, whether it is a missile, whether it is a spacecraft, whether it is a satellite, all these have a very important application areas for lithium ion batteries. However, another important area which is coming up is because of the renewable energy. We are generating a lot of power through our renewable source, either solar or wind or wave and so on. The storage is a very important issue there, storage of batteries. There are many different forms of storing electrical energy, but lithium battery once again is a very efficient storing device, and lithium, they are also important for as storage for renewable energy. So, lithium batteries along with solar energy is a very good combination, for generating power and storing it for the off periods. So, these are the important areas, and that is the reason this is one of the most active area of research, materials research so far or at this point of time. Current production level about 2 to 3 billion units per year, which is a very high level compared to many other batteries, is fairly large number. Okay. So, this is so far as the applications areas are concerned. Finally, we will come to what are the future directions. Future directions very interesting. There are two aspects as I mentioned, so far the developments are concerned. One is of course the anode and cathode material, and also the organic electrolytes. There are a lot of research is going on whether the electrolyte can be replaced by some other organic materials, better organic materials, but I have not discussed here that kind of work. What I want to point out here, we have discussed this as the cathode material, and we have seen some of the results where graphite has been used as the anode material, right. But there is a possibility in this also is a cathode material. Okay. This is also a cathode material which can replace lithium cobaltite, right, but its voltage is very low, it is about 1.5 volts or so. So, compared to graphite, if you compare with graphite and this becomes your cathode, then the voltage is about 1.5 volts, whereas compared to graphite this has a voltage of about 4 volts, very close to 4 volts, right, or 3.5 volts or so. Since the mechanism of both the materials, the lithium intercalation is more or less same, the attempts now being made whether this can be used as one of the electrodes or the anode. So, this can be used as one of the anodes. So, here which the material which was originally developed as a cathode material, now it is being used as an anode material. So, this becomes anode. So, completely replace graphite, this becomes your anode and this becomes your cathode, electrolyte remains same. So, this kind of a system will give you a voltage of about 2 volts, which is much lower than 3.5 volts normally available with lithium battery, but it is still a interesting system. It is still an interesting system, and lot of research is going on in this kind of with this kind of material, where 2 volts is low. So, the capacity will be reduced, but the materials are very abundantly available. One is titanium, iron, phosphate. So, it is not restricted by the non availability of cobalt. Of course, graphite is an abundantly available material, but it has its has some other problems. So, this is one system which is being tried out for the future systems, and of course, the charge discharge characteristics is important. So, although it has a lower EMF, open circuit voltage, but still this can be an attractive system to start with or investigate. Then you have another system, again the same material, but here the cathode is replaced, the same anode, but the cathode is replaced. So, you have about 2.5 volts. So, that the voltage can be increased to some extent. So, instead of lithium phosphate, iron phosphate, the cathode can be lithium manganite, the spinel structure, but the anode may be same. So, you have a possibility of increasing the voltage from 2 to 2.5. There is one more system which is also being thought of. This is once again the same anode. So, the anode has been common, but the cathode instead of manganese, only manganese or iron phosphate, we have this manganese has been replaced by partly nickel. So, lithium, nickel, manganese, and that gives you a voltage of about 3 volts. So, these are some of the systems which can be tried out, has been tried out, and people think that these are possibilities for the future. The most important thing in any of these, there is no cobalt in it. So, the cobalt is one of the bottlenecks, and that can be avoided in all these systems, and the volume change of the graphite, can also be avoided. Okay. So, one is the volume change of the graphite can be avoided here. If one sees the earlier curve, the volume change of the graphite is quite large here. So, that can be avoided, and if you go back to our earlier diagram of the possibility of different materials like this, here is this. I was mentioning earlier that this is which has been originally thought of as a cathode material compared to the graphite. Now, we are talking of this becomes your anode, and all these materials here can be used as the cathode material. So, you can see here is your lithium iron phosphate compared to this. So, this becomes the voltage here, this is 1.5 volt and this is close to about 3.5 volts. So, it becomes about 2 volts or 2.5 volts. Then you have this one is this couple is another one, and this couple is another one, this one and this one. Okay. So, this is another interesting direction in which the research is going on. So, it started with graphite and lithium cobaltite. Now, we are talking about different couples, different systems, okay. Different cathode, different anode and a different another cathode. So, this is what actually the development is. These are the three systems on which the work is now currently on, and maybe some of them are useful for the future generation of batteries and the future applications. As I mentioned, the future application, the main driving force is high power applications. The low power application is more or less gas saturated, the electronics application, but it is now the high current applications or high discharges applications which are of importance. So, with this we complete our discussion on battery, the lithium ion battery, and also the systems related to energy technology. Earlier we have discussed the fuel cells, then we have also discussed how the hydrogen can be produced using the advanced materials, some of the electrical properties of the advanced materials, and now we have just completed the discussion on lithium ion battery. As you can see, there are many different oxides and carbides as well as borides or nanocomposites which can be very conveniently used for these systems. So, it is materials research which is actually the key to the success of these energy technology systems. With this we come to the end of this lecture, and thank you for your attention.